Hello, welcome to our channel. My name is Laurent Schmalen and today I'm going to guide you to this small presentation showcasing some of our research results on communications using graph-based processing. In particular, we're going to show how we can use tools for machine learning and signal processing to improve some aspects of communications. In particular, I will address two topics in this presentation. One is the decoding of short channel codes for forward error correction, and the second one is the problem of symbol detection and how we can use techniques from graph-based processing to tackle this problem. All is based around topics in machine learning, and we probably all know that machine learning has had tremendous success in the past decade, let's say. And if you have ever looked and worked with machine learning, you have probably encountered the MNIST database. The MNIST database is a database of handwritten digits, and a very simple task is to recognize the digits in these handwritten digits. For instance, in postal applications, we can think of zip code recognition to route the letters. And with modern machine learning systems, we can now recognize more than 99.5% of those handwritten digits, which is quite a success story. Also, machine learning has revolutionized the field of natural language processing, image processing. This is just an example. This is very popular right now to build those little figurines from oneself. And we can also upload images. This is an image I took that we will see later in the presentation and just modified using just a few text-based prompts, and you can play around with this. And it's quite fun, but it can also be used for practical applications. So how can we leverage machine learning and tools for machine learning and communications? So we also had another video on our channel where we looked at how we can use machine learning for equalization in particular. In this talk, I'm going to talk a little bit about different tools and different topics and also slightly different applications. So where do we stand? We start with the first application, and this is the decoding of short channel codes. So why do we need short channel codes? And in particular, many modern applications require short channel codes. Examples are Internet of Things, IoT, machine-to-machine type communications, vehicle-to-vehicle or vehicle-to-X communications, control, telemetry signals, etc. Machine-to-machine type communications, we typically don't require a lot of data transmission. We don't transmit videos, we don't transmit images, but we transmit rather short packages, like just a couple of data, telling the machine to perform a new task, etc. Unfortunately, for those applications, we lack good and practical short channel coding schemes. So we have a couple of schemes, but they are not particularly good or they are not particularly efficient. So we need to work on finding channel codes that can be decoded efficiently in this regime for short block lengths. The question is, can we use tools for machine learning to improve both the code but also the decoder? Of course, the answer, as you can guess, is yes. Otherwise, it wouldn't be in this presentation. So let's take a deeper look at this. So we start with a very simple code, the read-Muller code. It's a very short code of length 32-bit. And the information length is 16-bit, so we just want to transmit 2 bytes of information. Could just be a simple telemetry comment to a satellite, for instance, or to a device. And this short code, this read-Muller code, because it's so short, we can actually carry out the optimal decoding. So what we see here in the graph is the block error rate or the error performance as a function of the signal-to-noise ratio, EB over N0, with an optimum maximum likelihood decoder, which we can calculate for this short regime, for this short block lengths, but typically it's not feasible in practice. Now if we use a practical decoder, and one very popular practical decoder is belief propagation decoding. Belief propagation decoding is a very versatile, low complexity decoding algorithm. There exist tons of applications, tons of implementations on hardware of this belief propagation decoder, and it works very well for large codes, for the long block length regime. Like for LDPC codes, it's very popular and it's very widely used and ubiquitous in many communication systems. Now, what is the performance of belief propagation decoding with this code? It's very bad. So it's not competitive. There is a gap of around 1.5 dB between the belief propagation decoding performance and the optimum maximum likelihood decoding performance. So the question now is, how can we improve this gap? What can we do to close this gap? So for this, we look a little bit deeper into belief propagation decoder. So what happens inside the decoder? So inside belief propagation decoding, we use a graphical representation of our code. And here you can see the graphical representation, and I have to point out and I have to emphasize that this graphical representation is not unique. So there exist multiple graphical representations of a single code. So now in the decoding, we use an iterative process. So the decoder is an iterative process that essentially takes this graphical representation, and each node of this graphical representation is a small computer. It's a small computing element, and it takes some messages, calculates a new value, and it passes these messages along the edges. So these nodes, we have two different types of nodes, which means we have two different types of computers. These nodes calculate some messages, and then they pass these messages along the edges to the other nodes. These nodes again compute some messages and pass them back. And we repeat this process back and forth until we converge to a result. So we pass messages from the blue round nodes to the square nodes, we pass messages back, we pass messages again, and we repeat this iteratively. Now, instead of iterating between the nodes, we can also unroll the graph, which means we don't iterate between the nodes, but we just put the different versions of the graph beneath each other. This is what happens here. So now we have a data flow from top to bottom. So what we do is we calculate messages. This is what we get from our channel. This is the input to our decoder. So we start by calculating the messages. They go to the square nodes. They calculate messages and they pass them again to the round nodes. But now we just assume that we have a copy of the round nodes and they are just put beneath each other in such an iterative flow graph. And we repeat this, in this case, 3 times. We have 3 iterations, and at the end we get some outputs. This is what is called unrolling of a graph. Now, this is a jump. What we now have is a neural network. So what you can see here is a neural network, and a neural network also looks very similar. In the neural network we have nodes. They are called neurons. These nodes, they are also small computational elements. They're small computers, they carry out a certain computation. So we get some input to our neural network, we carry out a computation, we pass it to the next layer or next nodes, we carry out a computation, and so on. We pass this to the network. So the neurons, the neural network consists of neurons. They typically apply weighted summation of the inputs followed by a nonlinearity, for instance a hyperbolic tangent. Now what we do when we say we train the neural network or we learn the neural network is we take these weights or weighted parameters and we optimize those using gradient descent. So we have weights with which we multiply the inputs, we optimize those weights, and we carry out the nonlinearity. So if we compare this neural network and belief propagation, we see that there is a striking similarity. Both are more or less the same algorithm under some disguise. Then of course the question is, can we use tools from neural networks in order to carry out belief propagation decoding? The answer is yes, and the resulting algorithm is the neural belief propagation decoding algorithm that has been proposed by Nachmani and Beeri. So what we do is we unroll the graphical representation of the code, as we have seen. Then what we do next is we augment the edges by some weights W. So instead of calculating some values inside these computing elements, we now take these values and we multiply them by some weight W. So if we look into the detail, we see that we take the input messages flowing into this node, we multiply them each by an individual weight, and then we calculate output messages. And you can see down below the reference where this algorithm has been first proposed, a very seminal paper that if you're interested in this topic, I highly recommend to read it. So now what we do next is we can define a loss function that we want to optimize. So for instance, we want to optimize the error rate, bit error rate, block error rate, etc. And then we carry out gradient descent to optimize the weights, or we use variants of gradient descent like Adam algorithm, etc. to optimize these weights. Okay, so what does that bring us? So if we take a look at the previous example, the Reed-Muller code that we had earlier, now we have the maximum likelihood decoding performance again, error rate as a function of the signal to noise ratio. This is the belief propagation decoder. And now with neural BP, we get quite a big performance improvement. So there is a significant performance improvement compared to conventional belief propagation. We have not fully closed the gap to maximum likelihood, to the optimal decoder, but we have gone quite far already. Now, what this decoder does, it's taking into account the fact that the messages that we send in this graph are not well suited for BP decoding. It's a suboptimal decoding and the messages may not be well suited. It does not account for the fact that the parity check matrix may not be well suited. So the matrix that we start with, this graphical representation of the code that we started from, may not be well suited. So what we can do is we can try to learn the graphical representation or the parity check matrix of the code that is best suited for decoding. How do we do this? We do this by starting from an overcomplete graphical representation that essentially represents more than is actually needed, and then we remove some nodes that do not contribute to the performance, to the decoding performance. So let's take a look at how this works. What we do is we start with an overcomplete parity check matrix. So overcomplete means we have actually more expressions than we need to represent the code. So if you look at these square nodes, they represent the so-called parity check equations of the code. So each square node is a so-called parity check equation, and what we do now is we introduce linearly dependent parity check equations. They are not needed to represent the code, but they give us some additional expressiveness. So if we look at the previous representation of the code, there we had 3 so-called parity check equations to represent the code, and now in the example we introduce 2 linearly dependent parity check equations, and we have a total number of 5. This is just for illustrative performance reasons. Real codes, they are much larger and have much longer, much bigger graphical representations. So what do we do now? The next step is we tie the weights at each check node. What does that mean? So if we look at the check node, we see that the outgoing messages that are computed by this node, they are multiplied by weights. For each weight going into some variable nodes, it is multiplied by weight. Now we say that all of those weights must be identical. That means we tie them, so they are identical. And they denote the contribution of each check node. So if you have a small weight, it means the output of this check node is not important. It does not contribute much to the following computations. If it's a large weight, it has a big influence on what's coming next. So then what we do is we do the following schedule. So we train the network, we find the least important check node, so the one that has the smallest weight, and we just remove it. So we kick it out. So in this example, it's this green node, and we remove it from the graph, like this. Now we have a new graphical representation. We repeat this again. So we train the network, we find the least important check node, and we remove it. So, and then we repeat this until the performance starts to degrade. So now, for instance, in the next step, this node has the least weight, and we remove it, and like this. And afterwards we end up with a graph that may look like this. So it means in each iteration we have different graphical representations. In this example it's always the same number of nodes, but this may also differ. We don't have any constraint on this. This is what we call a pruned neural belief propagation decoder. So let's take a look at the performance. So here we have again the error rate as a function of the signal to noise ratio. And now with our optimized decoder, we can outperform the neural belief propagation decoder by a tiny little bit, 0.4 decibels. So it may not sound like much, but it's an improvement. Now, what is also astonishing is that because of this pruning, we actually remove all those nodes that are not necessary, that don't contribute to decoding. So potentially we can also reduce the complexity. And this is what we see here. So the belief propagation decoder and the neural belief propagation decoder, they use 3,700 roughly operations in these square nodes. And these square nodes, they essentially determine the complexity of the decoder. Now, the optimized decoder only has 1,170 operations. So it's a significant improvement of the complexity. The complexity is reduced by a factor of more than 3. So this is very nice because at the same time we have improved performance and we have reduced the complexity. Now the question arises, does this also work for other codes? Yes, it also works for other codes. So here's an example of a Reed-Muller tree-7 code. This is a code that essentially has a code word length of 128-bit. And so we have 64 information bits, meaning 8 bytes that we can transmit. We carry out 6 decoding iterations, and we have a performance improvement of roughly 0.4, 0.2, 0.3 decibels. But at the same time, we have a complexity reduction by a factor of approximately 30. So we need significantly less complexity than the neural belief propagation decoder. So let's take a look at another class of codes, short LEPC codes. So here is another LEPC code. This is a code that is standardized by the CCSDS, which is a consultative committee for space and deep space applications. And this is a code that is, for instance, used to transmit telemetry data to satellites. And it's also a code of code word length 128. And it's a pretty good code. So it has a similar parameters than the Reed-Muller tree-7 code. And here you can see the Reed-Muller tree-7 code, in order to reach an error rate of 10 to the power minus 4, needs signal to noise ratio of 3.4 decibels. And with this code, we only need a signal to noise ratio of 3 decibels with an optimal decoder. So with an optimal decoder, we have a very good code. Now the question is, how does it perform with belief propagation decoding? Well, also not so bad. Not so good, sorry. So with belief propagation decoding, we see that there is a significant performance gap, almost 2 dB, between the optimal decoder and the belief propagation decoder. There are some approaches to improve this, using, for instance, ensemble decoding. We can improve it a little bit, but not so much. With this neural belief propagation also, we don't get a significant improvement, but in our other work that I will just refer to here, something that we published a couple of years ago at ICASP, we have a very good performance and we outperform the ensemble decoding based methods, for instance, and we can get to within 1 decibel of the performance of the optimal decoder. This is what we call a learned decimation algorithms. I will not go into the detail in this video because the algorithm itself is quite involved, but I will point you to the literature, which you can also find in the description of the video below. All right, so with this, we have wrapped up the first chapter or the first part of this presentation. Now let's take a look at the second part. Now we use this neural belief propagation algorithm for symbol detection, which is a completely different problem than channel decoding. But the same technique can be quite nicely used also in this other context. So What we do now is we extend this graphical representation a little bit, and we formalize this a little bit and we introduce a tool called a factor graph. Factor graph is a tool that is known in the literature, especially in classical machine learning, and it's a tool to represent a factorization of a function, essentially. So we have a function, for instance, we call this function p, and it's dependent on n input parameters x1 to xn, and we can write this function as a product of individual functions pj that depends on each on a subset of input parameters. So let's take a look at an example. We have a function p that depends on x1, x2, x3, and we can write this function as p1, which only depends on x1 and x2, p2, which depends on x1, x2, and x3, and p3, which only depends on x3. And then we can represent this factorization using a factor graph, which we can see over here. And this factor graph essentially takes the variables, these are called variables, it has the input parameters of the function x1, x2, x3, and we draw them as circular nodes. Exactly the same circular nodes as before in the decoder, because there we essentially also used a factor graph. And we have these square nodes, these are the so-called factor nodes, and they represent each of those functions. So function p1 depends on x1 and x2, which is why we have connections to x1 and x2. p2 depends on x1, x2, and x3, so we have connections to x1, x2, and x3. And finally, p3 only depends on x3, so we have only a connection to x3. So this is what is called a factor graph. So it's just a way of representing a factorization of a function. Now, why is that important? There is a very efficient algorithm, and this is the belief propagation algorithm that we have just encountered previously. It's a very efficient algorithm to carry out a marginalization of this function. So very often in communications we want to compute a marginalization, which means we want to evaluate the function at all possible values of x2 and x3, and then sum up the results in order to get a marginal p of x1. So the marginal p of x1 is defined as the sum over all the other possibilities of all the other variables except x1, summing up this function. And the belief propagation algorithm is a very efficient tool of calculating this marginalization, and it gives us this result in very little complexity. And if this factor graph has no cycles, it's even the optimal way. So how can we use this factor graph for a communication problem? Well, we look at the task of symbol detection. So what is the task of symbol detection? We want to transmit symbols, and these symbols are taken from some alphabet M. And this alphabet has a cardinality of capital M. So, for instance, this is a constellation, QPSK, BPSK, 16QAM, etc. So it's complex symbols that we take from an alphabet, and then we transmit them over a channel. What does the channel do? The channel does a convolution with an impulse response H, and it adds additive white Gaussian noise AWGN. So in the channel, we have a convolution of the input sequence with the impulse response, and we add additive white Gaussian noise. We have received symbols Y, and now the task is to carry out symbol detection, and the symbol detection should give us posterior probabilities P of X given the sequence Y, and by taking the maximum or by maximizing the posterior probabilities, we do an maximum a posteriori detection, and we get hypothetical transmit symbols X hat. And so the objective of the symbol detection is actually to find these posterior probabilities, and the posterior probabilities can be expressed as a marginalization problem. So it's a marginalization over P of the sequence X given Y over all possible symbols except the one at position K. And it can be expressed as this expression, so it's a summation and a product and some terms that are due to the Gaussian noise. Now this is very difficult to calculate. If we want to calculate this for all possible sequences, it's essentially an infeasible task. But we would like to use belief propagation to carry out this task more efficiently. So we can use the factor graph representation, and it's a factor graph based equalizer, by essentially writing P of x given y, so this probability distribution, as a product of these terms. So we have a factorization. And we can draw a factor graph, because now we have a factorization of this probability P of x given y. And the factor graph looks like this. This is a so-called Forney style factor graph, and it's drawn down here. So we have the circles, they are essentially the symbols that we like to transmit, and the squares here, they are the function nodes. They are this, essentially represent this function. And these function nodes, they depend on L plus 1 different variables. So each function node depends on L plus 1, and here L is equal to 2, so on 3 different variables. And L is the length of the impulse response of our channel. Okay, so we can say a problem is solved. We just run the belief propagation algorithm on this graph and we are done. Well, it's not so easy, because unfortunately the complexity of evaluating these square function nodes scales very unfortunately. And it scales with the cardinality of the constellation to the power L plus 1, and L plus 1 is the length of the impulse response. So if we have a high order constellation, 16 QAM, 64 QAM, 256 QAM, we already have a very large M. And then if we have a long impulse response, multiple symbols, the complexity becomes infeasible. So the scaling of this complexity is unfortunately not feasible. So we need to simplify this a little bit. How can we simplify? One ingenious way of simplifying is to rearrange this factorization a little bit and to introduce something called preprocessing. So preprocessing means we take our channel output and we first multiply it with a preprocessor, which is essentially just we take the sequence and we apply matrix multiplication with the Toeplitz matrix. This can be a matched filter, but it can essentially be any matrix, it can be any convolution that we do. And when we apply such a preprocessing, we get the so-called Ungerbock factor graph representation. If you're interested, we have a reference below where you can read more about this Ungerbock factor graph representation. And the Ungerbock factor graph representation looks like this. So we again have our variable nodes on the top and we have our factor nodes on the bottom, and now we have two types of square nodes. And each of those carries out a different computation. We have the red ones, they are called F nodes. They carry out this computation, or they are responsible for this computation. And we have the blue nodes, they're the I nodes, responsible for this, just on top of my head, representation. The nice thing we see is that the maximum degree of each factor node now is 2. So we have 2 connections at most, and these number of connections determine the complexity. And the complexity of this Ungerbock factor graph based equalizer grows with Lm squared. So the length, it's linear in the length of the impulse response, and it's polynomial in the constellation size. And this is very good because this leads to very low complexity equalizers. Question is, does it work? This is a little bit disappointing because it works for some channels, but it does not work in general. So here we show an example. First, we have a Proakis B channel. This is a very widely known channel, and here is the frequency response of this channel, and we see that it has a low pass characteristic. And what we show here is the bit error rate as a function of the signal to noise ratio again. Again, for this channel we can calculate the optimal detector, so the MAP detector. This is the best we can do. This is with BPSK modulation. If we apply the Forney style factor graph, remember it has complexity which goes as m to the power L plus 1, we get very good performance. We get within a couple of fraction of dB compared to the optimal performance. If we apply a traditional linear equalizer, we get this performance, so already significantly worse. Now if we apply the BP algorithm to the Ungerberg vector graph, the performance is very bad. It's also not a bug, it's really for this channel, performance is very bad. For other channels it works perfectly, but for this channel, performance is bad if we don't modify it. Now the question is, how can we modify it? And the answer, of course, is we use null belief propagation. So now we apply null belief propagation to this, detector based on the Ungerberg vector graph. And what we get is we get an optimized preprocessor P, and we get also weights inside. And for this channel, we see that with the optimized or null BP applied to this Ungerberg vector graph, we get a low complexity symbol detector that performs close to the optimum. So very, very close to the MAP detector. And this also works for some other channels. We also have other techniques on how to improve or how to modify the Ungerberg vector graph based equalizer or symbol detector using different techniques, all based on null belief propagation. And if you're interested, I will also link the 2 papers that we have in the description below. So let's take a look, or let's recap again what we knew. So we have introduced 2 types of vector graphs for symbol detection. First, the Forney style vector graph. It has high complexity, but for many channels with plain BP without any modification, it offers near MAP performance. On the other hand, we have the Ungerberg vector graph, the UFG. It has only low complexity. It does only have factor nodes of degree 1 and 2, so very low complexity, but with plain BP it can have very poor performance. So the performance heavily relies on the vector graph structure. This is something we can summarize. This is also something that has been noted in the literature. We have different ways of representing a factorization, different vector graphs. Performance of BP heavily depends on how this vector graph looks like. And unfortunately, if we have a factor node degree, so the number of edges connected to the factor nodes, here it's 2, determines the complexity. So we don't want too many connections. So the question is, how can we leverage this? Or can we kind of trade off, find a good trade-off? Can we optimize the structure of the vector graph? For this, we introduce a simplified version of the vector graph. So we don't distinguish between the nodes anymore with colors, but we use these smaller boxes, we use these larger circles just as a different representation of the vector graphs. And now the idea is, can we create new representations of this vector graph by clustering? And clustering means we generate new vector nodes, like these square nodes, by grouping them together and interpreting them as a larger degree effective node. And we apply this to the Ungerberg vector graph. So here's the idea. So we apply clustering. So we have this vector graph with 3 vector nodes, and now we take 2 of those nodes and we represent this as a new node f4. So for instance, if we have this factorization of the function f1, x1, x3, f2, x1, x2, and f3, x3. Now we group those 2 functions into a new function f4, which now depends on x1, x2, and x3. This is just a different way of expressing this factorization. This is something we can do and can include in this. We can just modify this as we like. So either we have the full factorization or just this partial representation where we cluster the nodes. Now the question is, how can we find those clusterings? How can we optimize this? So for this, we take a look at what we call factor node containers, because these factor node containers, they transform this clustering problem into systematic form. So we start with the Ungerberg vector graph. This is our basis for clustering. And then we introduce containers. So these containers, they are empty factor nodes and into which we can factor those clusters. So here we introduce containers. They have a degree of 3. So they have 3 connections. And now we can assign some of those factor nodes into these containers. So for instance, we can take this node and we can group it to container 9 to container 10. So the factor node can be clustered into the containers and the containers that connects to the same variable nodes. And we create a new factor graph by putting all the factor nodes into one of the options or in one of these containers. So the problem, however, is that this is a combinatorial optimization problem. So we have many possibilities and this is very difficult to solve. So the way to solve this is we relax the problem, we apply relaxation, and this is what we call continuous clustering. And it's explained in the reference below. The idea is that instead of assigning a factor node to a cluster, we assign it simultaneously in all of the options. So how does that work? It works by essentially saying that we factorize the functions into multiple options. So this function fi can be written as the product of the function fi to the power alpha j if the sum of those alpha j is equal to 1 and they are between 0 and 1. So meaning we can have a function fi, we can express it as the square root of fi times the square root of fi. So fi to the power 1/2 times fi to the power 1/2. Because we are dealing with probabilities, this is possible because we have no negative values. And so by interpreting fi as a product of fi to the power alpha j, we can assign, for instance, this yellow factor node, we can assign it to 2 clusters, one with power alpha 3 and one with power alpha 4, and the sum of those alphas must be equal to 1. So we assign a little bit to it, you can say a little bit is assigned to this cluster, a little bit is assigned to this cluster. And now we optimize these weights alpha I. And we use gradient descent. So we use tools from machine learning to optimize these values alpha I. By the target is to minimize the bit error rate. So we can do this, and this is what we get. So here we have the performance of the MAP detector, so the optimal detector. This is now a modified channel, so it's a slightly different channel than we had before. We introduced some zeros, changing the frequency response, but essentially it's a very similar channel. The yellow curve is the Forney-style factor graph with a high complexity. It has maximum factor node of degree 5. And this is the Ungerberg factor graph with low complexity with factor node of degree 2. And now, if we allow containers of maximum degree 3, we get a performance improvement. So we learn how to group the factor nodes of degree 2 into new factor nodes of degree 3. By this, we get a performance improvement. Essentially, if you know a little bit more about BP, you know that the performance is restricted by short cycles in this factor graph. By grouping and doing the clustering, we essentially get rid of some small cycles. This is what we do. If we allow containers of maximum degree 4 here, then we get this green performance curve. So again, we get another performance improvement. We can of course apply null belief propagation decoding to both of them, and then we get a further performance improvement by just applying plain null BP. So now we approach the performance of the MAP decoder. And we can also apply pruning. So we have these alphas. They indicate again the contribution of each factor node to the final result. If we have a little contribution, if alpha is close to 0, it means the factor node to the power alpha is close to 1. It has little contribution to the final product. We can remove it. And here is just an example of what we get. So the final graph. We have some nodes of degree 2, we have some nodes of degree 3, we have some nodes of degree 4. So this is just the example graph that we get after pruning for this channel. So with this, I'm already at the end of this presentation. So let's give you a quick outlook, let's conclude the presentation. So we saw that machine learning, and in particular the technique of neural belief propagation, which is a combination of classical machine learning, where the belief propagation algorithm is from, and modern machine learning with neural networks, can overcome many difficulties that we have in factor graph-based signal processing and factor graph-based detection, decoding. The advantage of factor graphs is that we have a unified model, and this unified model can lead to very efficient implementation. It's a graph-based processing. We can define small computing elements that exchange information in a graph, which is very easy to implement and which hardware, people working in hardware actually like. I could only give you a glimpse on what is possible. So we have applied this to phase noise compensation. The same technique can be applied to signal processing algorithms in fiber optic communications. One example is phase noise compensation. We have used this for decoding quantum LDPC codes that are necessary in quantum computing, where the traditional VP algorithm is also very inefficient. And we have extended this also to new update rules. We have introduced non-extrinsic neural belief propagation, and we have proposed joint blind channel estimation and symbol detection, where we learn the channel and we carry out symbol detection at the same time. So I will also put references to these papers in the description below. I will also link some of the videos that we did on those topics, and I welcome you to watch this if you are interested in this topic. You can always contact us if you want to get more answers or if you want to collaborate. So with this, we are at the end of this presentation. I thank you for your attention, and I would like to take the opportunity to acknowledge the students who have contributed to this. So it was Andreas Buchberger from Chalmers University of Technology, Lukas, who did this as a part of his master thesis, and Luca, who also did this as part of his master thesis and his PhD thesis. And I also like to acknowledge funding. Funding was from European Research Council and from the Federal Ministry of Education and Research in Germany in the scope of the Open6G Hub project. So with this, I'm at the end of this presentation. I hope you enjoyed it. Please take a look at the description. I link additional material. I link other papers that you can take a look at. And I would be very happy if you find this interesting and if you like to start working on this topic. Thank you very much.